Have you ever tried to slide a heavy box across the floor? It can be quite difficult to get it moving. There is an invisible force working against you. This force is called friction. Friction is a contact force. It happens when two surfaces touch each other. It always tries to stop motion or prevent it from starting. Think of it as a resistance. Without friction, things would be very different. Imagine a world with no friction at all. If you pushed a book, it would slide forever. Cars wouldn't be able to start or stop. You wouldn't even be able to walk. Friction is essential for many everyday actions. It helps us grip things and move around. Friction arises from the microscopic roughness of surfaces. Even surfaces that look smooth are not perfectly flat, they have tiny bumps and ridges. When two surfaces press together, these bumps interlock. This interlocking creates a resistance to movement. Let's explore this fascinating force a bit more. Friction isn't just one single thing, it actually has different types or faces. The first type we'll talk about is static friction. Static means not moving. Static friction is the force that prevents an object from starting to move. Imagine that heavy box again. When you first push it, it doesn't budge. That's static friction holding it in place. It matches your push, up to a certain limit. If your push exceeds this maximum static friction, the object will start to move. Once an object starts moving, a different type of friction takes over. This is called kinetic friction. Kinetic means related to motion. Kinetic friction is the force that opposes the motion of a moving object. It's usually less than the maximum static friction. This is why it's often harder to get something moving than to keep it moving. Once the box starts sliding, kinetic friction is what you're working against. Kinetic friction itself can be divided further. There's sliding friction, like the box sliding on the floor. There's also rolling friction, which occurs when an object rolls over a surface. Understanding these types helps us predict and control motion. Now let's switch gears a little. Let's talk about objects that move in circles. This is called circular motion. It's a very common type of movement in the universe. Planets orbit stars in nearly circular paths. A merry-go-round at the park shows circular motion. When you swing a ball on a string around your head, that's circular motion too. It's a special kind of motion because the direction is always changing. Even if the speed is constant, the direction isn't. An object moving in a circle is always changing its velocity. You might think velocity just means speed, but in physics, velocity includes both speed and direction. So, if the direction is changing, the velocity is changing. And if velocity is changing, that means there's acceleration. This might sound strange if the object's speed isn't changing, but acceleration means any change in velocity, including just direction. So, an object in circular motion is always accelerating. For an object to move in a circle, something must be constantly pulling it towards the center. This is a key feature of circular motion. We said that an object in circular motion is always accelerating, and this acceleration is directed towards the center of the circle. According to Newton's laws of motion, if there's acceleration, there must be a force. A force is what causes a change in motion or an acceleration. For circular motion, this force is called centripetal force. Centripetal means center-seeking. This force is always directed towards the center of the circular path. It's the invisible hand that keeps an object on its curved trajectory. The centripetal force is not a new kind of force itself, rather, it's a role that other familiar forces can play. For the ball on a string, the tension in the string provides the centripetal force. For a planet orbiting the sun, gravity provides the centripetal force. It's whatever force is responsible for pulling the object inward. This inward pull continuously changes the object's direction. It keeps the object from flying off in a straight line. Without this centripetal force, circular motion cannot happen. Understanding centripetal force is key to understanding any kind of circular motion. Section 5. Friction. The secret to staying on a circular path. We've learned about friction, and we've learned about circular motion and centripetal force. Now let's connect these ideas. Friction plays a very important role in many cases of circular motion. Often, friction is the very force that acts as the centripetal force. It's the secret ingredient that allows objects to turn or move in circles. Without friction, many circular movements we take for granted would be impossible. Consider a cyclist leaning into a turn. What keeps the bicycle and rider from skidding straight ahead? It's the static friction between the tires and the road surface. This friction provides the necessary inward centripetal force. The cyclist leans to help balance the forces, but it's the friction that does the crucial work of changing direction. Think about walking around a circular track. Each time you push off the ground, you are using friction. To change your direction and follow the curve, you rely on friction. This friction between your shoes and the ground points towards the center of your turn. Section 6. How strong is friction? A simple calculation. We know friction is important, but how strong is it? Can we measure it? Yes, we can. Physicists have ways to calculate the force of friction. The maximum force of static friction is usually what we focus on first. This is the force needed to start an object moving. It depends on two main things. First, the types of surfaces in contact. Second, how hard the surfaces are pressed together. Scientists use a special number called the coefficient of friction. This coefficient is represented by the Greek letter mu. It's a measure of how rough or sticky the two surfaces are relative to each other. A higher mu means more friction, like rubber on concrete. A lower mu means less friction, like steel on ice. There's a coefficient of static friction, ms, for objects at rest, and a coefficient of kinetic friction, mk, for objects in motion. The other important factor is the normal force. The normal force, N, is the force pressing the two surfaces together. The basic formula to calculate the maximum static friction, Fmax, is Fmax, equal sign m is asterisk n. Section 7. Friction in circles in our world. Everyday examples. Friction's role in circular motion isn't just a textbook concept, it's happening all around us every single day. We've already mentioned cars turning corners. The static friction between tires and the road provides the centripetal force. This is why road surfaces are designed to offer good grip, and why tire treads are important, especially in wet conditions. The treads help channel water away, maintaining contact and friction. Without sufficient friction, safe cornering at normal speeds would be impossible. Think about running on an indoor track. Many indoor tracks have banked curves. The banking helps runners make the turn. Part of the normal force, when a surface is banked, points towards the center of the curve. This component of the normal force assists friction in providing the centripetal force. This allows runners to take curves at higher speeds. Even so, the friction between their shoes and the track surface is still crucial. Consider a satellite orbiting the Earth. Gravity provides the centripetal force for them. But for objects moving in circles within our atmosphere, friction can be a factor. Section 8. Fun with friction. Amusement park physics. Amusement parks are fantastic places to see physics in action, especially friction and circular motion. Many rides spin you, swing you, or send you around curves. Think about a classic spinning ride like a carousel or a faster spinner. As the ride spins, you are in circular motion. What keeps you on the ride? If you are sitting on a seat, static friction between you and the seat helps. It provides part of the centripetal force needed to keep you moving in a circle with the ride. Consider a ride like the rotor or gravitron. In these rides, you stand against a wall, and the whole room spins. As it spins faster and faster, you feel pressed against the wall. Eventually, the floor might even drop away, but you don't fall. What's holding you up? It's static friction. The wall pushes inward on you, the normal force. This normal force, combined with the coefficient of friction between you and the wall, creates an upward static friction force. This friction force balances your weight, keeping you pinned to the wall. Roller coasters are another brilliant example. They have thrilling loops and tight turns. When a roller coaster car goes through a loop, it's undergoing circular motion. Gravity, the track's normal force, and sometimes friction, all play roles. For the car to stay on the track in a loop, there must be sufficient centripetal force. Section 9. The adventure of physics. Keep exploring. We've journeyed through the world of friction and circular motion. We started by understanding friction as a fundamental force, a force that resists motion between surfaces. We saw how it has two main faces, static and kinetic. Static friction prevents motion from starting. Kinetic friction opposes objects already in motion. These concepts are vital for understanding how things interact. From simple pushes to complex machinery, friction is always there. Then we explored the fascinating realm of circular motion. We learned that moving in a circle means constant acceleration. This acceleration is always directed towards the center of the circle. This requires a special force called centripetal force. This center-seeking force is what keeps objects on their curved paths. It's not a new type of force, but a role played by existing forces. Gravity can be a centripetal force, and so can tension, and very importantly, so can friction. Friction often provides the necessary centripetal force. It allows cars to turn corners and people to walk around curves.